Hello, welcome back for the second and last part of the feedback video on for the breadth paper 2024 Chemistry AS. Um, let's go. Let's go quick. So we have this question: the student investigates the rate of decomposition of H2O2 on addition of MnO2 catalyst using a gas syringe. We get the results. Draw a line of best fit and circle the anomalous result. This one is pretty obvious. And then we're going to use our graph to determine the rate of reaction at 50 seconds. So first, we're going to draw our line of best fit. Okay, it's approximately like this. And don't forget to put a circle around the anomalous result. Some of you forgot. It's an easy mark to win. It's an easy mark to lose. Make sure you put the obvious anomalous result. Then if we want to measure rate of reaction at a given time, we're going to have to draw a tangent. So you're going to draw it, you don't have to be perfect, but it has to be approximately nice and perpendicular to the curve. So I just drew my tangent here, and I'm going to use 2 points to calculate the slope or the gradient of this tangent. I've marked my 2 points. One is at 0.22, the other one at 50.53. To calculate the rate of reaction, it's going to be the change in volume divided by the change in time. I've put my value, 53 minus 22 divided by 50, and I found a value of 0.62 centimeter cube per second. You have a range of possible answers for this, so it has to be close enough to 0.6 for you to get the marks. And make sure you show you're working on the graph, otherwise you will lose the mark. Next, the student used 50 centimeter cube of H2O2 in the experiment. That's a solution of aqueous H2O2. And that's going to decompose into water and O2. Calculate the concentration of H2O2 required to produce 90 centimeter cube of O2 at RTP. So if we work at RTP, we know that 1 mole of gas occupies 24,000 centimeter cube. Therefore, we can calculate the number of mole of O2 produced by dividing the volume, 90, by 24,000. And that is 3.75 times 10 to the power of minus 3 mole of oxygen produced. From the equation, we know that the number of mole of H2O2 divided by 2 is equal to the number of mole of O2 divided by 1. Therefore, the number of mole of H2O2 required is 2 times the number of mole of O2 produced at the end, which is 7.5 times 10 to the power of minus 3 moles. So we have the number of mole of H2O2 needed. We have the volume of H2O2 solution, 50 centimeter cube. We can calculate the concentration by doing the number of mole divided by the volume. Don't forget to divide 50 by 1,000 to convert it in decimeter cube, and you should find 0.15 mole per dm cube of H2O2. A student's plan to compare the rate of decomposition of H2O2 using different metal oxides as the catalyst. Thing that should be kept constant, thing that should speed up the reaction, is the concentration of H2O2, the surface area of metal oxide, the temperature of H2O2, and the mass of metal oxide. I would go for the concentration and the temperature as your first two, then the surface area of metal oxide and the mass of metal oxide for last. And each of those would give you a mark. Finally, a bit of organic chemistry. So here we had to name the product for the reaction of butanene with bromine. So you'd have the 1,2-dibromobutane. Then the reaction of butanene with hydrogen in the presence of a nickel catalyst. You will add 2 hydrogen to each carbon of the double bond to form the butane. Then with the reaction with H2O in the presence of an acid catalyst would form either the butan-1-ol, that's going to be your main product, or the that's going to be the minor product, or the butan-2-ol, which is your major product. Okay, you need those 4. It didn't have to be displayed formula. You could have done the skeletal formula or semi-displayed. It is up to you as long as you have the right product. HBr reacts steadily with alkane. Outline the mechanism. So when you draw the mechanism, please make sure you add the relevant dipoles and the curly arrows properly. So step 1, you are going to have your delta positive H, which is going to be attacked by the double bond, and the bromine is going to gain this pair of electrons because it's more electronegative. You're going to form a carbocation and a bromide ion, and in the final step, the bromide ion will form a covalent bond with the positively charged carbon to form the 2-bromobutane. Okay, make sure you have the delta plus, delta minus. Make sure you have the curly arrows in the right direction, starting from the pair of electron always. Make sure you have the right product, and make sure you have the positive charge on the carbon, please. Then, during the reaction, a small amount of 1-bromobutane is produced. Explain why 2-bromobutane is the major product. So when forming the 2-bromobutane, you are going to use a secondary carbocation. Only one hydrogen is bonded to the C+, and it's more stable than the primary carbocation involved in the formation of 1-bromobutane. And that's why the 2-bromobutane is the major product. Final question. We have all this information. We have to identify X. Step 1, calculate the empirical formula. Same as always, you're going to use the percentage to calculate the number of mole of each of your element. Here we end up with a ratio of 1, 1.33, and 1. If you have a situation like this, you know you need to multiply all the numbers by 3 to get a whole number for hydrogen, and we have an empirical formula of C3H4O3. Step 2, we need to calculate the molecular formula. To do that, we're going to look at the mass spectrum, and we have the last peak at 88. Okay, so we know that the molar mass of X is 88. The molar mass of C3H4O3 is also 88. Therefore, the molecular formula of X is C3H4O3. Then we're going to look at the infrared spectrum of X, and we have a very broad peak around 3000 centimeters minus 1. That is the OH of a carboxylic acid group. We also have this peak around 1700 centimeters minus 1. That is the C double bond O. So we know that we have a COOH group, and therefore we must have another C double bond O somewhere. So we have two possible structure. The first one, the aldehyde and the carboxylic acid group, or the second one, the ketone and the carboxylic acid group. To choose between the two of them, we're going to go back to the mass spectrum. And here we can see at 15 there is a little peak here. And the peak at 15 we know is caused by a CH3 plus fragment. And the only way to have a CH3 plus fragment is if we have the ketone and the carboxylic acid group. Therefore, the only possibility for X is this CH3COCOOH. All right, guys, this is it for me. Hope you enjoyed that. If you have any questions, please let me know. In the meantime, have a lovely summer, and I will talk to you very soon. Bye bye.